Suppose we have a regression test score equals a function of the student-teacher ratio and the percent English language learners following our Stock and Watson example. We're familiar with the hypotheses that the coefficient on student-teacher ratio, beta 1, is equal to 0, or the null hypothesis that beta 2, the coefficient on English language learners, is equal to 0. And we know how to test each one of those individual hypotheses. We test them by constructing the t-statistic. The t-statistic is the estimated coefficient beta 1 hat divided by 0, our null hypothesis, and divided by the standard error of beta 1 hat. And that t-statistic, we know from a variety of assumptions, if our sample size is large, that the t-statistic follows the standard normal distribution. So the probability of observing an absolute value of a t-statistic greater than 1.96 is less than 0.05 because it follows the standard normal distribution. So there is a small probability that if we observe a large t-statistic, so if we have a t-statistic from our sample that turns out to be greater than 1.96 in absolute value, then we reject the null hypothesis. The p-value is less than 0.05, and so we should reject the null hypothesis because it's very unlikely we would observe a coefficient of that magnitude, a beta 1 hat, and a standard error of that magnitude, whatever it is that we observe, if the null hypothesis were actually true. So we should reject the null hypothesis. So those are individual hypothesis tests, but sometimes we have a joint hypothesis test. We want to test the hypothesis that beta 1 is equal to 0 and beta 2 is equal to 0. That is, that both are 0. That is, that neither affects test scores. So that's a different kind of hypothesis, and we need a slightly different method to test that hypothesis. So, but it's going to be very analogous to the t-statistic. We're going to construct a statistic that we're going to call the F statistic. T-statistic, F statistics, not that different, not that hard, right? This F statistic has a formula, but the actual formula is very complex. We are not going to be able to look at what the actual formula is in the class. We need matrix algebra for that. We'll look at some simplified versions if we make some assumptions like homoscedastic errors or there's only two restrictions. Our joint hypothesis is a very simple joint hypothesis. Then we can see what the formula is for the F statistic. But regardless of whether we know what the formula is, like the t-statistic, if the F statistic is large, then that means that our null hypothesis that both beta 1 equals 0 and beta 2 equals 0, that null hypothesis is unlikely. So if the F statistic is very large, then the null hypothesis is unlikely and we should reject it. We might say, well, how unlikely? Well, R, our statistical computing software, will calculate a p-value for us of this F statistic, a p-value of the F stat. If the p-value of the F statistic is less than 0.05, our usual criteria, then we should reject the joint null hypothesis. So it's pretty straightforward, very similar to using the t-statistic to test a hypothesis about a single coefficient. Let's look and see how we do this in R. So following our schools example, here is the code in your t-multireg tutorial, right? t-multireg.r. So the command's very simple. It's the LHT command. Pepper wants to go out of the room. Excuse me. So it's the LHT command. Then the first thing we have in the option is which regression we're going to test the hypothesis on. So in this case, it's the results from Reg 5. Then we have our hypotheses. So our first hypothesis is that meal percent is equal to 0 and CalWorks program percent is equal to 0. So we have two coefficients on those two variables. We could have 3, we could have 4. So you see that each one is has a comma. They have quote marks. So you have to be very careful in making sure that the syntax is followed. It's a single equal sign. So this is two restrictions. That is a joint hypothesis test that meal percent is equal to 0, the coefficient on meal percent is equal to 0, and the coefficient on CalWorks percent is equal to 0. We could have 3, we could have 4 restrictions. We could have other kinds of restrictions too. So you'll see in the tutorial there's a variety of restrictions. Don't worry about this. This is just telling it that we're not assuming homoscedasticity. Rather, we are assuming the broader heteroscedastic structure of the errors. So we run that command. After we've run the other commands, of course, the regression command, we need reg5 there. And then this is our output. And we see right here, here's our p-value for the f statistic, and it's 2.2 times e to the negative 16, so 0.16 zeros, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? This is obviously a lot smaller than 0.05, so we are going to reject our null hypothesis that both of them are equal to 0. So we're rejecting the null hypothesis that they're both equal to 0. So that means one of them is not equal to 0. It could mean that both of them are not equal to 0. We can't know that from our hypothesis. All we can know is that at least one of them is not equal to 0. We can reject that, that hypothesis, right? Sorry, we can reject the hypothesis that both equal to 0, but of course one of them could be equal to 0 and the other one not equal to 0. And we see, as usual, there's asterisks there indicating the level of significance. And that's really all we're going to see with this F statistic. If you're reading the table, this right here is the number of the F statistic. It's a little off to the side. So that's the F statistic, and this is the p-value of the F statistic.